Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at approximating solutions to analytic equations. So in this section of the course, we are going to be looking at approximating solutions to analytic equations, and we will describe how this topic specifically includes differential, integral, and integro-differential equations. However, we will then explain why we are going to be focused entirely on differential equations, including ordinary and partial differential equations. And we will give an overview as to the approach we will be using throughout this section. Now, in your calculus course, you've already been introduced to two flavors of differential equations. The first being ordinary differential equations, or ODEs, and the second, partial differential equations, or PDEs. Now, together with differential equations, analytic equations also contain integrals. Now, engineers focus on differential equations, but all the techniques we are covering are also applicable to differential equations, integral equations, and interdifferential equations. We'll look at some. Now, an ordinary derivative is a derivative of a function of one variable with respect to that derivative. Now, in this course, we're using the first notation. A partial derivative is a derivative with respect to a function of two or more variables with respect to one of those variables while holding all other variables constant. Basically, partial differentiation assumes that there are no dependence between the different variables. Now, partial derivatives can be represented either as follows. In the first case, we have a partial with respect to x of this function of three variables. On the right, we have a partial with respect to t of the same function of three variables. In this course, we're going to use this notation. Another notation may be as follows. Here we have a function of, well, 2, 3, or 4 variables where the second variable is actually a vector. So it could be a vector that is one-dimensional, two-dimensional, or three-dimensional. And in this case, we are taking a partial derivative with respect to that function with respect to the first variable of the vector. Now, a differential equation is an equation that involves an unknown function of a specific variable, and that equation can also include that variable, and it also may include the derivative of that function or higher derivatives. Here we see an RL circuit, and applying Kirchhoff's voltage law, we get that the differential equation that describes this is the one you see here. An integral equation involves an unknown function and its integrals. So once again, if you apply Kirchhoff's voltage law, you get this integral equation. Finally, an interdifferential equation involves an unknown function, its integrals, and its derivatives. Here is an RLC circuit, and there is the corresponding interdifferential equation. Now, by taking derivatives, integral and interdifferential equations can be converted to pure differential equations. So, for example, if we differentiate this with respect to t, we get the following second-order differential equation. Similarly, Maxwell's equations can be written either as integral equations or as partial differential equations. So, for example, Gauss's law in integral equation form is shown here, while in differential form is shown here. Now, to make life simple, engineers simply focus on differential equations, and that's what we will be applying in this course. Consequently, in this section, we are going to be looking at how to approximate solutions to problems involving ordinary differential equations, including initial value problems and boundary value problems. And we are going to be approximating solutions to problems involving partial differential equations. Specifically, we're going to look at the heat equation, the wave equation, and Laplace's equation. Now, throughout this section, this is the approach that we will use. In every single case, we are attempting to approximate a continuous and differentiable function. We can't approximate such a function everywhere. Instead, what we will do is we will approximate the value of the function at specific points for the argument, and then we will interpolate for values in between. So, for example, if we are trying to approximate a solution that is a function of one variable, what we will do is we will try to find approximate values of the function at points t sub k for specifically chosen values of t sub k. We will then find approximations at these points. If we wanted to find the value of the function somewhere between these points, we could then use interpolation, for example. If we are finding a function that is of two variables, then we will approximate this function only at specific points again, t sub l, x sub k, and we will find approximations u sub lk that approximate the value at t sub l and x sub k. Following this topic, you now have an understanding and an overview of the ideas that will be covered in this section. You are aware that analytic equations include differential, integral, and integro-differential equations. You understand that in this course, however, we will focus on ordinary and partial differential equations, and we have described the approach we will be using. That is, we will approximate continuous functions by estimating the value of those functions at specific points, and then we'll use interpolation or some other technique to find values of the functions between those points. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!